Have you ever stopped to think about how much our world is constantly changing? I mean, from a simple rusting gate to a spectacular firework, everything is transforming. And believe it or not, there's this hidden language, this fundamental code that describes all of it. So today, we're going to crack that code. All right, let's start with a little riddle. What could cooking an egg and a rusty old nail possibly have in common? I mean, they seem totally different, right? But deep down, at their core, they are basically the exact same kind of process.
And the answer? They're all chemical reactions. And it's not just them either. Think about it. Milk going sour, grapes fermenting, food cooking on the stove. Heck, even the food you're digesting right now, or the very air you're breathing, all of it, every single one, is a chemical reaction happening all around us all the time.
Okay, so chemical reactions are everywhere. We've got that down. But what does that term actually mean? Let's dig in and find out.
So, a chemical reaction is basically a process where the stuff you start with turns into something completely new, with totally different properties. It's not like tearing a piece of paper, right? That's just a physical change. You still have paper. No, this is more like burning that paper. You can't get the paper back. You're left with ash, a fundamentally different substance.
And to keep things organized, chemists use two super important words. The stuff you start with, that's called reactants. And the new stuff that gets made, we call those products. It's really just a simple before and after story. Reactants go in, products come out. Easy.
So, how can you tell if you're actually seeing one of these transformations in the wild? Well, you gotta be a detective. Look for the clues. Maybe you'll see a solid turn into a liquid. That's a change in state. Or a change in color. Sometimes you'll even see gas bubbling up, or feel things get hotter or colder. These are all dead giveaways.
Okay, so we know how to spot a reaction. But trying to describe one in plain English, it can get really long and clunky. That's why scientists came up with a universal shorthand. And that brings us to the really cool, elegant language of chemistry. I mean, listen to this. When a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide. Okay, yeah, that makes sense. But wow, it's a mouthful, isn't it? For scientists who do this all day, it's just way too slow.
So the first step to simplify this is what we call a word equation. It's pretty straightforward. On the left, you've got your reactants. In this case, magnesium and oxygen. Then there's an arrow that points the way. And on the right, that's your product, magnesium oxide. See? Already so much better, right?
But wait, we can take it even one step further. Let's make it even better. Instead of words, we use chemical formulas. So now it's just Mg plus O2, arrow, MgO. This is the true language of chemistry. It's short, it's precise, and anyone, anywhere in the world who knows the code can read it. But hold on a second. If you look closely, this first draft, what we call a skeletal equation, has a tiny little problem. See the O2 on the left? That's 2 oxygen atoms. But on the right, in MgO, there's only 1. It's like an oxygen atom just disappeared into thin air. And in chemistry, that is a huge no-no. And that brings us to maybe the most important step in writing this code correctly, what I like to call the great balancing act. And we have to do this because we have to follow one of the most fundamental, unbreakable laws of the entire universe. And that is the law of conservation of mass. It sounds fancy, but it's a really simple and powerful idea. You cannot create matter, and you cannot destroy it. It just changes form. All the atoms you start with have to be there at the end. They just get shuffled around into new partnerships. Think of a chemical equation like a perfect inventory sheet for atoms. The number of atoms of each element on the left side must be exactly the same as the number on the right. The books have to balance, no exceptions. Okay, let's actually try to balance one. We'll use a method that's basically just trial and error. Now, the number one rule is you can't change what's inside the boxes. Those formulas are locked in. You can only change the number of molecules you have. All right, let's start with the most complicated part, that Fe3O4. Look at the oxygen. We've got 4 on the right, but only 1 on the left in the water molecule. So let's put a big 4 in front of the H2O. Great, oxygen is balanced, but whoops, now we have 8 hydrogens on the left. No sweat. We just go to the right side and put a 4 in front of the H2. Now hydrogen is balanced, and finally, the easy part, 3 irons on the right, so we just stick a 3 in front of the Fe on the left, and we're done.
Let's do a final check.
a little inventory. On the left, 3 irons, 8 hydrogens, 4 oxygens. On the right, 3 irons, 8 hydrogens, 4 oxygens. It's perfect. It's balanced, and it follows that all-important law of conservation of mass.
Awesome. So now that we know how to write and balance the language of chemistry, let's look at how scientists actually organize the millions of different reactions out there. They don't try to memorize them all. Instead, they sort them into a few basic categories, kind of like how a biologist sorts animals into groups like mammals, reptiles, and so on.
First up, we have the combination reaction. This one is exactly what it sounds like. You take 2 or more simple things, and they combine to form one single, more complex thing. The basic recipe is just A plus B gives you AB. A perfect everyday example is burning coal. You've got carbon, which is C, plus oxygen, O2, and they combine to give you carbon dioxide, CO2.
Now, on the complete flip side of that, we have the decomposition reaction. As you can probably guess, this is where one big, complex thing breaks down into 2 or more simpler little things.
So the recipe for this one is AB breaks down into A plus B. A really great example of this is when you heat up limestone, which has the chemical name calcium carbonate. That big CaO3 molecule breaks apart into calcium oxide, CaO, and carbon dioxide, CO2.
You know, this whole chemical code thing, it's not just some abstract exercise for a science class. It's literally the operating system for the entire physical world. Once you know how to read it, you start seeing it in action absolutely everywhere.
The breath you just took? That's respiration, an exothermic reaction. That shiny, hard finish you see on a whitewashed wall? That's a combination reaction happening right there. And your stomach breaking down your last meal? That's just a whole series of decomposition reactions. These are all things we can now understand and describe using this amazing chemical language. So think about what we've just done. We've learned how to spot reactions, how to write them down in their own special language, how to balance them so they follow the laws of the universe, and even how to sort them into different types. You literally now have the key to cracking the code of change, to understanding the transformations that shape our entire reality. So the only question left is, what secrets are you going to unlock next?